Real exam questions. This is question three. It's about the design of beams. The question goes as follows. A beam with a width of 300 millimeters supports a floor slab in an office building. The concrete quality is C4045 and the steel quality BE500. The characteristic value of the uniformly distributed load on the beam, QD, is 53 kilonewton per meter as a permanent load, including the self-weight of the beam, and 27 kilonewton per meter mobile. Take care of it. It's put in characteristic value. Determine the height of the beam and the tensile reinforcement, the number and the diameters, that guarantee a concrete compression height equal to 0.28 times the D. It is not permitted to use bundled bars, so the steel bars must not be touching each other, but reinforcement in 2 layers is allowed. Determine the total height of the beam within 5 millimeters. So the effective span was 7 meters, and the stirrups have a diameter of 10 millimeters, and the concrete cover is 40 millimeters. So this is the cross section. We know the width is 300 millimeters. We don't know the total height. Simple bending, so we neglect the contribution of the compression reinforcement and the tension reinforcement. Point of gravity is D1, which means is the concrete cover of 40 plus the stirrup diameter and plus the point of gravity of the tension reinforcement that we still don't know. The diagram of the strain, we know it's domain 2A because X is given as 0.28 times D. It's domain 2A because it's simple bending. Sometimes this is required because it means that they most likely they will form up a reservation into the beam going like that. So a reservation in here. So they want to make sure that this section is under compression and this section is under tension. So that is requested 0.28 D. We know the compression strain at the top, which is 3.5 per mil. But we do still, at this moment, do not know the strain or the stress or strain in the reinforcement. Corresponding stresses, this is for the concrete compressive strength. It's on this side, X, we know what X is, but we do not know what is the lever arm. So because it's domain 2A, we see immediately that in domain 2A, the compressive strain is 3.5, and the steel strain must be smaller than 10 per mil. The filling coefficient is 0.81, and the coefficient center of gravity is 0.416. We know this because this is in domain 2A. The position of the neutral axis is Xi, is X over D, and with the uniform triangles, we find immediately what is the strain in the steel. And we find it's 9 per mil. The total design load on the beam is the mobile load times 1.35, is the permanent load, times 1.35, plus the mobile load times 1.5, and it gives you 112.05 kilonewton per meter. The bending moment is then, of course, Q L squared over 8, which is 686 kilonewton meter. From that, we can calculate in dimensional units. The equilibrium equation is then mu d times c times 1 min delta g c. We know those two values, and we can now substitute it in the equation, and we find a, uh, um, a reduced bending moment of 0.2. First, we check if this is in area 2A. So we know this is in area 2A when mu d is 0.2. The design value of the compressive strength is then 0.85 times FCK divided by the material factor. Note that 0.85 is required in the annex of the national annex of Belgium. That's why we are using this. So the total design value of the compressive force is 22.7 megapascal. From this equation, we can now derive the needed effective depth. So take in mind that for the units, so we work always in Newton and millimeter. That's why it's 10 to the power 6 added. And we have 710 millimeters. The lever arm zeta is equal to z over d. Z is d minus delta gx over d, or it is 1 minus delta g times c. All of those values we have already, we can calculate. So the zeta, and we got 0.8835. From this, we will calculate the needed reinforcement, and we find for the needed reinforcement 2,516 square millimeters. It is a lot of reinforcement to be put into a beam of only a width of 300. But this is the case here, the width is given. So after some trials, we find that 8 diameters 20 gives you 2,513 square millimeters. This is close enough. This is okay. But we have to look how are we going to put those 8 diameters 20 into the cross section. First, look how many bars can we put horizontally in one layer. So that means that the width B, which is 300 millimeters, must then be bigger than the concrete cover, which is 40 on both sides, stirrup diameter 10 on both sides, and then we have the 4 diameters 20 plus the space between those reinforcement bars, which is 40 millimeters. So it gives you a total of 300. So this is fine. So we can only put 4 diameters 20. So taking care that the distance between the reinforcement must be at least 40 millimeters. So we need 2 layers. The distance between the 2 layers is of course also 40 millimeters. And from that's the position of the 8 diameters 20. We can now calculate the point of gravity, which is of course concrete cover plus stirrup diameter plus half of the clear distance, which is 40 divided by 2, and plus the diameter that we use. So the point of gravity of the 8 rebars in tension is 90 millimeters. The total height or total depth, sorry, of the beam is then D1, 710 plus D710 plus D1 gives you 800 millimeters. So the answer is the dimensions of the beam are 800 times 300 millimeters. And this depth of beam is needed to guarantee a concrete compressive zone equal to 0.25 times B. Now this whole calculation can also, of course, be done by using concrete tables. We take the right table for concrete classes smaller than C50-60, and the maximum allowable strain in the tension reinforcement is 10 per mil. Now, what is given the design value of the position of the neutral axis is 0.28, and so we know it's domain 2A. We see in this table this is Xi, which is 0.28. So we see immediately from the table that the strain in the concrete is 3.5, and in the steel it's 9 per mil. And from this table, you see also that C and delta G is, of course, in zone 2A, it's 0.81 and 0.416. We can now directly see what is mu D, which is 0.2. We know that mu D is defined by this formula. And from the table also, you can immediately deduce that the mechanical reinforcement ratio is 0.2263. From this, we can subtract D. We can calculate D, and it gives you 710 millimeters. And from this equation, we can, with the definition, we can find the total needed reinforcement. You see that in this formula, there is FYD. So take care of that, because it is FYD. You can see it here. The steel is yielding. If the steel is not yielding, and it is smaller than 435 megapascal, then we have to adapt accordingly. So the total amount of steel needed is 2,512. So you see we have the same result, but using the tables, it can go very quickly.